Hello, my name is Victoria Drake, and I'm a third-year chemistry major at the University of West Florida, currently conducting research under the direction of Dr. Karen S. Molick. Our research is focused on the detection of real-world samples using surface-assisted laser desorption ionization, or SALDI, mass spectrometry. Quinine, as shown in Figure 1, is a low molecular weight biomolecule historically used to treat malaria. Traditional hard ionization mass spectrometry techniques make it difficult to detect low molecular weight biomolecules, such as quinine, because the hard ionization can fragment the molecule past the point of identification. SALDI mass spectrometry is a soft ionization mass spectrometry method that is ideal for low molecular weight biomolecules because it reduces fragmentation and helps with clarity of samples. Transition metal oxides, or TMOs, are specifically used in this research as an inorganic nanoparticle surface because they require minimal sample preparation, have low surface area to volume ratios, which help with signal-to-noise ratios, and they are compatible with a wide range of different analyte solutions. This is beneficial in analyzing impure compounds like seen in the real world. An analyte solution was prepared by combining 10 millimolar of quinine with a standard analyte solvent consisting of a 1:1:2 solution of acetonitrile to molecular water to 0.1% trifluoroacetic acid, or TFA. The TFA was used to create a cation species of quinine. For the tonic water samples, the solution was spiked with pure quinine to account for the difference in concentration. A nanoparticle slurry was prepared by using 20 milligrams of each of the 4 nanoparticle samples and 1 milliliter of nanoparticle solvent, consisting of a 1:1 solution of acetonitrile to molecular water. The analyte solution was then added to the nanoparticle slurry and plated using the dry droplet method. Figure 2 shows a desorption ionization mechanism associated with SALDI. The laser pulse hits a dry droplet sample consisting of the nanoparticle surface situated beneath the analyte. The surface helps desorb the laser energy and the sample becomes ionized with reduced fragmentation. The nanoparticles used in this research were small and large iron 2,3 oxide and small and large cobalt 2,3 oxide, with the small and large particle sizes shown in Table 1. Figure 3 shows the rebuilt laser desorption ionization reflectron time-of-flight Bruker mass spectrometer with vacuum system. 50 laser pulses of each dry droplet nanoparticle well were recorded with a nitrogen laser at a wavelength of 337 nanometers. The flight tube was kept under constant vacuum at around 10 to the -7 torr. The mass spectrometry data for the pure quinine in 4 different nanoparticle surfaces is shown in graphs 1 through 4. All 4 of the nanoparticle species spectra shown detection of quinine N plus H at around 325 grams per mole, and the dimer 2N plus H at around 650 to 651 grams per mole. Table 2 shows the signal-to-noise ratio was higher in the small cobalt 2,3 oxide than in the large cobalt 2,3 oxide. Figure 2 also shows that the large iron 2,3 oxide had greater signal-to-noise ratio than the small iron 2,3 oxide. In comparison, the mass spectrometry data for the quinine and tonic water for the 4 different nanoparticle surfaces is shown in graphs 5 through 8. All 4 of the nanoparticle species spectra shows detection of quinine N plus H at around 325 grams per mole. The dimer was not able to be detected in the tonic water samples. The Table 2 comparison of signal-to-noise ratios for tonic water mirrored the signal-to-noise ratios for pure quinine between the nanoparticle species. Although the tonic water samples mirrored the pure quinine samples with matching nanoparticle surfaces, the tonic water samples did show an overall decrease in signal-to-noise ratios as well as intensities compared to the pure quinine samples. Overall, the transition metal oxide nanoparticles showed to be an effective surface for the detection of biomolecules in real-world samples, such as tonic water. The large iron 2,3 oxide was the most effective surface with the highest signal-to-noise ratio and intensity in both the pure quinine sample and the tonic water sample. The large cobalt 2,3 oxide was the poorest transition metal oxide surface because it had the lowest signal-to-noise ratio and intensity for both the pure quinine sample and the tonic water sample. I would like to thank the University of West Florida, the University of West Florida Office of Undergraduate Research, the Hall Marcus College of Science and Engineering, and the National Institute of General Medical Sciences of the National Institute of Health.